Let's now look at the functional form for a standing wave. Now, the book is going to call this first bit the amplitude function, so we'll come to that in the next slide. Note that we have a sine and we have a cosine, but that one is of a function of position, one is a function of time. When we had a traveling wave, we had sine, but its argument included both position and time. So instead of having one sinusoidal function that depends on both position and time, we now have two sinusoidal functions that actually are going to include one being position and one being time. So now specifically calling this second one cosine versus sine just has to do with what your initial conditions are, so don't worry too much about that choice per se. If you wanted to, you could just call this sine and then have a different phase offset. So notice that this case, our entire amplitude is 2a, right? So the maximum value you ever have is 2a, and in this case, lowercase a corresponds to the amplitude of each traveling wave. So if you wanted to say, well, what is the overall amplitude of your standing wave, the maximum value you ever get is 2a. So you could call that a different variable if you wanted. We have angular frequency, omega, and this matches the angular frequency of whatever our traveling waves were. K is the wave number, which again matches the wave number of what our traveling waves were. But we can still talk about a wave number or a wavelength, an angular frequency, a normal frequency f, or a period. We can still define all of those things for our standing waves. The only thing that we really have to think a little bit different about is, again, that the amplitude changes a little bit. And again, the last thing to note is we can talk about an amplitude function, which is going to be this 2a sine of kx. So that amplitude function is effectively the maximum envelope that you're going to get. So that's what the book is talking about when it talks about the amplitude function. So it's helpful to think about what's happening separately in our position and in our time. When we think about what's happening in time, this is effectively a number that's going to be between -1 and +1, including 0 in between. So there are certain moments in time where this term equals 0, and that corresponds to this, right? So certain moments in time, it's here. Other moments in time, this is -1. So if I take this -1, that might be multiplying whatever that sine of kx is by -1. We have a different moment in time where it's +1, that would then be the positive version. So what's making it go up and down is the cosine of omega t. But then this outer function, what it's being multiplied by, is that amplitude function. So again, there's kind of this sinusoidal shape, but it is going up and down in time. So hopefully that makes a little bit of sense here, that there's what the shape is, so again, where we have sine in space, and then the up-down as well. So you have to keep track of both time and space in a very different way than the traveling wave. The next thing we can look at here is the location of nodes. And remember, again, really important, that node is where it's 0. So if we just look at the amplitude function, again, the node location doesn't change in time, so we only need to think about the spatial representation. The node is where this equals 0. And so that gives us a condition on kx. And we can say that this must then be 2 pi. And remember that just k becomes 2 pi over lambda. So 2 pi x over lambda, which is the same as k lambda, must be equal to these specific points. Now what is this? So keep in mind that this was our wavelength. And so if we look, we're going to have nodes again at wavelength over 2 and wavelength. So another way to write this is that you're going to get these special points at integer numbers multiplied by lambda over 2. And the reason for that is that if you plug in, for instance, lambda over 2 for x, you get kx equals pi. Sine of pi is 0. If you plug in 0 sine of 0 is 0, and so on. So if you plug in these special values where it's lambda over 2, lambda, 3 lambda over 2, and you plug that in for x, that will make kx give you an integer value of pi. So another way we can write this is that the condition is that this must equal m times pi. M is an integer and it can include 0 here. So 0, 1, 2, 3, and so on. So those define the places where you actually have your nodes. So there's going to be problems where you think about the node spacing or location of the nodes, and you're going to actually need to use this. What we haven't talked about yet is the idea boundary conditions, and if both of your ends are held down, if it's a string, what that means is you must have nodes on each end. That's going to allow only certain types of standing waves. So that will be covered in a future video.